Hello, everybody, and welcome to another lecture of ATMO 412. First of all, how are you guys doing? I hope you're doing well. I hope you're all staying healthy. I hope your families also are doing well. As usual, if you need anything, pasta, toilet paper, kitchen towels, or anything else, please feel free to reach out for anything. And do not leave your house unless it's strictly necessary. I know that spring has come. Though here it's always kind of nice. But spring has come. The weather is great, and we may be tempted to go to the beach. But please wait before you do that until the pandemic is gone. The beach will always be there, so we can wait. We can wait a few more weeks. Today's topic for ATMO 412 is kind of in line with what we discussed last time. If you remember last time, we were talking about deep convection, and we talked about the basic ingredients of deep convection. Today, we want to put all these ingredients together into what is probably most relevant, or what is very relevant to forecasting the weather in mid-latitudes, which is more or less what we are interested in for the purpose of this class. Today's topic will be mesoscale convective systems. As we said at the very beginning of the class, synoptic scale, which is what we've been concerned with so far, is of the order of 1,000 kilometers, and that's what you should think of when you think about extratropical cyclones and atmospheric fronts, at least in the sort of along the front direction. Mesoscale is about an order of magnitude smaller and of the order of 100 kilometers. And it's where these convective systems typically exist. They're called mesoscale convective systems for a reason. What is so different between a mesoscale convective system and just a regular thunderstorm like the ones that we discussed last time? Well, if you remember last time, I'll try to do this calculation on the fly. Let's see if it works. But last time we talked about updrafts. Cumulonimbus clouds are essentially, just one giant updraft that goes up. We gave some kind of orders of magnitude, and we said, well, order of magnitude of the updraft is about 10 meters per second, let's say, which is 36 kilometers an hour. In some places, it's more intense than others, but let's keep this as a good order of magnitude. The troposphere, which is typically where thunderstorms live and spend their life, is about between 10 and 16 kilometers, more or less. So let's be generous. Let's say 18 kilometers, which is a lot, but let's be generous. I feel generous today. And also it's easier to do that, to do the math. 36 kilometers an hour for 18 kilometers, that's about half an hour, okay? Which means that an air parcel that reaches its level of free convection and suddenly can go all the way up can reach the top of the troposphere in about half an hour. And after that happens, the cloud is gone. The thunderstorm is over, right? And so this could be a significant event, but it's going to last for half an hour. Okay. However, thunderstorms have a way to organize and conspirate such that two thunderstorms can help generate another one. Do you remember in the last class we talked about convective triggering, meaning when two or more cold pools come together and create a new cloud? Well, these cold pools may very well be generated by another thunderstorm, by two thunderstorms. So you have two thunderstorms, generate two cold pools. The cold pools come together and create another thunderstorm. So now, if we were to think of the entire population of cumulonimbus clouds, well, this can keep going on even though each individual cumulonimbus cloud would last only about half an hour. Okay, so the reason, or one of the reasons why we're so concerned with mesoscale convective systems is that these can live for many hours and sometimes even days. Okay, so let's start having a look. Essentially, mesoscale convective systems, by and large, are a cluster of cumulonimbus clouds that develop some kind of circulation and cooperation on the mesoscale. So think 1,000 kilometers. They are much larger in extent and also much longer than usual thunderstorms. And there are certain areas in the tropics where mesoscale convective systems account for most of the rainfall. If you think of a region like the Sahel, which is this semi-arid region between the equatorial, really green Africa and the Sahara Desert, so it's like 10 north, give or take. Mesoscale convective systems are super important for the Sahel to generate rainfall. Sometimes we also talk about mesoscale convective complexes, and these are typically really cold-topped, really long mesoscale convective systems. Now we will see a little bit of the main features and characteristics of mesoscale convective systems. So definitions are always hard when it comes to these kinds of natural phenomena, because it's hard to, it's not a black or white issue. It's hard to tell when something stops being an isolated thunderstorm and becomes part of something greater in a way. But people have come up with some simple definitions. This is an example taken from Bob Howe's book called Cloud Dynamics. And this distinguishes defines what a mesoscale convective complex is. It's not so important that you remember all these details. Just keep in mind sort of the length scales that are involved. So, for example, here we're talking about a cloud shield, for example, that is over 100,000 kilometers squared. So that is 10 to the 5th kilometers. The square root is about, 300 kilometers? 333.333 kilometers. Did I say that correctly? Anyway, it's of the order of 300 kilometers. Pardon my math at the moment. So this should give you a length scale for these convective complexes. Okay. In terms of the place where these happen, they're actually quite widespread in the world. The figure here, the dots are counts of mesoscale convective systems over a certain period of time. The shading represents OLR. OLR stands for outgoing long wave radiation. The idea is that if there's no cloud, then short wave hits the ground, heats it up, and the ground reflects back some long wave radiation, and so you'd have a lot of outgoing long wave radiation. If you had a cloud in the atmosphere, either the short wave doesn't come in or it's trapped and reflected back somewhere else, and so you wouldn't have a lot of outgoing long wave radiation. So where you have very little, so white-ish colors, that's where you'd expect. Where you have the shading, so grayish areas. That's where you should expect the more sort of cloud coverage. If we look at the points, we can see that there are a few areas where these convective systems are important. The first one that we see, this is a Eurocentric map, more or less. The first one that strikes the eye is precisely the Sahel, which is this region in Africa that is really, really important and one of the most important regions in the world in terms of the way that the land interacts with the atmosphere. This is a complicated topic that I'll be happy to talk about outside of this lecture. If we look at the U.S., the Great Plains, more or less, seem to be an area where a lot of these mesoscale systems happen. We have some actually in Central America. My knowledge of geography is admittedly really poor, as you guys have all discovered, but I think that should be Colombia and Costa Rica on the side of the Pacific Ocean, where there are a lot of MCSs. Argentina also has a fair share. Argentina is not... I don't think it gets enough credit for having a lot of severe weather, because whenever we say severe weather, we think about America and, America number one in terms of tornadoes. And that's certainly true. Tornado Alley is like one of the worst places for tornado and supercells. But South America is actually in second place for occurrence of supercells. And then there is some in India, Bay of Bengal, China, not so many on the maritime continent, so Indonesia and Malaysia, and there is some in Australia. But by far, I would say Sahel and Central America, these are tropical regions that we're not so concerned with for this class. And then Great Plains and South America, these are two places where a lot of MCS is. So, for our class, we're thinking about weather forecasting for the mid-latitudes. We're thinking mainland a lot of the times, while MCSs are big players for that region. In terms of when these things happen, well, the timing kind of depends on where you are. And it also depends on what phase of the storm you're thinking about. First of all, here we see, on this figure, we see two arrows. The first one is the land, the top, and the bottom one is the ocean. First column is when the first storms initiate. So these kind of start to bubble, the bubbling, the MCS is like brewing and it's kind of bubbling these storms. Then the initiation, when the MCS kind of kicks in and some degree of organization develops. Then the maturity with the maximum extent, third column, and fourth column is the termination. Obviously, these happen in stages, and so you should expect them to happen one after the other. The land, notice how the land has a clear peak for each one of these phases, and the ocean kind of doesn't. One of the reasons why this happens is that MCSs over land are driven by and large by surface sensible heat fluxes, particularly in arid regions like the Sahel, or to some extent the plains as well. And these fluxes are tied to the sun, which have to shine in order for these fluxes to be there. The sound you hear has nothing to do with me. My neighbors are like washing their car. I don't know why, given that we can't go anywhere, but they're washing the car. So that was, in case you're wondering, just for transparency. So the land has a very small heat capacity. And so if nothing is shining on the land, then it cools down very rapidly. If something shines on the land, that you can get really, really hot really quickly. But you need that source, because otherwise heat is lost almost immediately, and that's why the land has such clear peaks in when these things initiate. It's interesting that the peak is, these MCSs really develop in late afternoon, which is kind of interesting because you would expect that these MCSs would start, the first storms would initiate at midday when the heating is the strongest. Why is this not the case? This is a big question, actually. And it has to do with the way that convection starts, deepens, it creates cold pools and downdrafts. The details of this process of deepening of convection are not clear. They're not known to date. But they're very, very important in delaying the onset of these MCSs. Needless to say, global models that have poor resolutions and that need convective parameterizations do an admittedly terrible job at predicting the time of this onset of the MCSs. So this, as you can imagine, very active area of research. I'll be very happy to talk to you, to talk your ears off outside of this class. The ocean has some peaks, but they're not as clear as the land. Reason being that the ocean water has a much larger heat capacity than the land, and so sure, the sun helps heating up the boundary layer over the ocean, blah 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 blah. But the ocean maintains its temperature after the sun is gone. Okay. In terms of sizes and duration, this is a distribution. These are two distributions that were done by looking at global numbers and numbers over the ocean or over northern and southern hemisphere. These are the four lines that you see here. As you can imagine, areas and duration kind of vary because it all depends on where you are and the dynamics. But the mode of the distribution of areas is about 200 to 150,000 square kilometers. And for the duration, the mode is about 10 hours. Probably the median is more towards 15 hours. But notice that there are some that can go almost all the way to 24 hours. So you have MCSs that last 24 hours. Keep in mind that one thunderstorm lasts half of an hour more or less. Okay, so it doesn't last long. So it's not trivial. But this is what convective organization can do. It can help these systems propagate for hours and hours and hours. One example of a mesoscale convective system, and sort of the poster child of convective organization, at least in the mid-latitudes, if you ask me, is the squall line. I don't know if you're familiar with this term, but squall lines are precisely what their name suggests. They're lines of thunderstorms. And convective organization acts to generate a structure for these squall lines. If we look at this slide, this is also taken from the wonderful book by Bob House, which I cannot recommend enough. First of all, there is a front of the storm, which is where the H1, L3 kind of are. That is where convection is most active. Then there is above and to the front of it, there is some high clouds, okay? And below this region, well, there is a very, very long cloudy region, okay? First of all, sorry, I keep saying first of all, so at some point we'll have to proceed to a second of all. So second of all these L's and H is that you see in the figure, these refer to local maxima of high and low pressure. So maximal pressure or minimal pressure. What happens? The storm is moving to the right, and as it moves to the right, there is a cold pool in front of the convective cells. The cold pool hits and sort of lifts, if you remember the mechanical forcing, lifts whatever air parcels that it encounters. Typically with squall lines, there's always a little bit of wind shear blowing against the squall line. So these, essentially, the combination of two, blow up a new air parcel. This air parcel becomes part of the convective region, which can be really, really intense. And then what happens? Well, as the parcel goes up in the convective region, it goes up and it kind of dies off because it's precipitated out all that it had to precipitate out, and it kind of faints away. And in fainting away, it is left behind because the squall line is moving. The parcel that we were following is kind of left behind, but a new parcel is coming in to sustain the convective part. So the convective part keeps going and moves forward. As the parcels kind of go up and quietly die in the back, they're still precipitating a little bit, kind of drizzling, doing some kind of a stratiform rain that we'll talk about in a minute, but they're kind of left behind. And so they create this really, really, really long region of stratiform clouds. In the figure, you also see, so you see the lines that point to the gust front, which is what I said before. And to the back, you see that there are these ascending front to rear flow. So this is kind of what I was just discussing now, these air parcels that are going up and kind of, sort of dying off. And then there's the descending rear inflow jet. This is essentially the equivalent, we'll talk about this, but it's the equivalent of the downdraft, of the convective downdraft for the stratiform region. You are going to have a downdraft in the convective region, that's for sure. But also, the stratiform region is kind of drizzling a little bit. Drizzle goes down, evaporates, cools the air descends. They have different intensities. The stratiform downdraft and the convective downdraft, they have different intensities. Equally important, though. One thing that I wanted to mention is that, as my neighbor continues to wash his car, which is getting really, really clean, and I'm very happy for him. There's a key ingredient in making the right squall line, because if you just throw air parcels against a gust front, you're not guaranteed to have something that can sustain for many hours. And really, the secret sauce here is that there has to be a good balance between all the vorticities that are at play here. Okay, let's proceed with calm. Consider the top panel of this figure that we're seeing here. To the very right, there is the wind. The arrows represent the wind. All the wind looks the same at all heights. Okay, no wind shear. Then you have the cloud. The cloud goes up, and you can kind of imagine the thermal that in going up, it has two vortices kind of associated with it. Okay, vorticity of different signs. And then there is the gust front that is kind of hitting or lifting the cloud. The gust front also has a vorticity because it has a circulation inside. You have two cyclonic vorticity and an anticyclonic vorticity. The two don't really balance each other. Okay? And so what happens is that the cloud doesn't really tilt in the right way. It doesn't rain as much out. And so the squall line doesn't live. This cloud that is going up will not generate a cold pool that will reinforce the existing one. The bottom panel, so let's skip the middle panel. The bottom panel, now the wind is not uniform anymore, but has a really, really strong wind shear. Wind shear means the wind is different at different heights. dW, dx in this case, there's no y direction. So this, you see immediately, this is vorticity. This screams vorticity from everywhere. However, the vorticity is too strong. Let's say the gust front is too strong, for example. And so the vorticity provided by the environment is not enough. This also disrupts the balance, and it kind of kills the squall line. In the middle example, on the other hand, you have the squall line that is propagating. The wind shear provides the right amount of vorticity. When all these vorticities balance, then the convective cloud can kind of ascend and go straight up. Okay? And when it goes straight up, It generates a really, really nice updraft, a really nice downdraft that then creates the right downdraft. And it's essential that the downdraft has the right amount of the right speed, because that will then control the properties of the downdraft, will then control the cold pool. And if the cold pool is too strong, is too fast, it's going to cut out the inflow to the squall line. If the wind shear is so the sound, it almost kind of sounds like elephants singing. So maybe we could think of elephants singing instead of my neighbor washing his car. So if the vorticity is unbalanced, for example, you could have a cold pool that cuts off the inflow to the squall line, or you could have, for example, a cloud that tilts too much and it generates too weak a downdraft, for example. And so when you have the right ingredients that typically depend on the thermodynamic conditions that will then control the cold pool and the vorticity in the cold pool, because they control the intensity of the cold pool, and also the wind shear, which provides vorticity into the environment, then you can have the perfect squall line that can live for a very long time. So this mechanism of like balancing vorticities is known as the Rotuno-Clamp-Wiseman, or RKW, and it goes back to a theory that was made by these three people in 1988, 1989. So what makes a good mesoscale convective system? We just saw now that squall line has a convective part and a stratiform part. This is kind of similar to all mesoscale convective systems. The main difference is that squall lines are typically more aligned against, well, a line, for lack of better words. And so squall lines tend to have a particular shape. Mesoscale convective systems can also have more of a blob-ish nature, blob-ish form. But essentially what these are going to made of pretty much all the time is a convective part, so convective towers, and there can be many of them, and there is a stratiform part. Precipitation in convective towers is due to the fact that you have really buoyant updrafts that condense and, get rid of a lot of rainfall. This is where the heaviest precipitation is typically found, okay, within these systems. So largest precipitation rates are typically found in the convective part. Because of the excess buoyancy that generates the updraft, and because of the high precipitation, you can typically have really strong updrafts and downdrafts in the convective part. This is an example. This is from a radar scan, and you can kind of see, if you look at the arrows that indicate, this is for a tropical squall line, but squall lines have similar features, maybe different intensities, but similar features in the tropics and in the mid-latitudes. And you can kind of see the convective part as the air kind of enters the squall lines at like a distance of about 10 kilometers, okay? So this kind of shows pretty much the structure of the convective part. These figures are another visualization of that. The top one shows vertical velocity, so this gives you a better idea of the velocities involved. The bottom one is reflectivity. Reflectivity is, as you probably know, is an indication of rainfall and rain rate. So greater reflectivity means a lot of rain. So it may be harder to see here, but the beginning of the squall line, kind of the entrance of the squall line, is a distance, the 40 kilometer distance, okay, more or less. At kilometer 20 is where the convective part is really strong. And to the left of all this is the stratiform part. Notice vertical velocities of, positive vertical velocities above 4 kilometers of altitude of the order of 4 meters per second or even more. To the bottom, 4 kilometers, there are downdrafts that are actually quite substantial. 4 meters per second downdraft. It's pretty good. It's pretty good downdraft. Also look at reflectivity. We have 50 dBz near the convective part. In the stratiform part, the reflectivity is about 20 dBz. Also, the negative velocity in the stratiform part, this is where you'd have the rear inflow jet. That's a lot smaller. So, we have peaks of 1 meter per second, negative 1 meter per second, but it's typically an order of magnitude smaller. So, the order of 0.1 meter per second. You guys want another example? Well, here you go. This is another example where now we're looking at the pressure perturbation that is due to the propagation of the system. Now, at distance 0 is pretty much where you have the entrance of the squall line. Notice that there are 2 regions. At -6 kilometers near the surface, there's high pressure, and there is a low pressure at -12 kilometers distance and 1.5 kilometers. Okay, so the one at -6 kilometer, that's usually also known as the meso high. This happens because right there you have, and also a little bit behind it, you have a strong downdraft that is coming down. And so the downdraft that is coming down is creating this jet. It's pushing and squeezing a lot of air next to the surface. This creates high pressure. Okay, common feature of all these systems. Behind it, where you have that convection is suddenly picking up. Convection picking up has exactly the opposite effect, and so it creates a depression. Also, processes that happen of condensation also create a lowering of the atmospheric pressure. This is another, these are, again, some few schematics of the squall line. They pretty much contain the same message that the others had. So if you want to spend some additional time, I recommend you pause the presentation now if you want to look at them in detail. Otherwise, we can move on. We move on looking at the convective part, focusing on the convective part. Now, what I'm showing here is a radar scan, essentially, of a squall line. Now, not all squall lines are, look beautiful like the cartoons that I showed you. Sometimes the stratiform part is not right behind the convective part, but is, maybe at an angle or is to the side or something like that. That often depends on why the elephants keep singing. That often depends on the wind shear, how the wind is blowing, because you have to imagine these things when they happen in the mid latitudes, Great Plains, there is always some form of wind shear that is blowing. Wind shear means that the wind changes intensity, but it can also change direction, right? And so you may have wind is blowing in this direction near the surface and in this direction in the mid-troposphere. And so air kind of goes into the squall line, but then is blown at an angle. And so when the air parcels dies off, it doesn't die off behind the convective part, but dies off at an angle. And so wind shear determines the orientation of the stratiform and the convective part. Convective part can be really rapid, can move at like 10 meters per second. And when you look at it on the radar, you just can't miss it. It's just so clear. Red color, there's no scale here, but red colors obviously indicate stronger precipitation. As we said, this is where you're probably going to have the highest flash rates, highest precip. They're naturally going to be here, and leading that, you're going to have the cold pool. This is another example of this, and it shows an interesting thing that, as you may have imagined, nature is never completely uniform. So if you remember when we talked about the vertical velocities within a convective cloud, we said, well, there's a lot of variation. There's a lot of variability within a convective cloud. And so, an airplane kind of shakes when it goes through it. Well, the same kind of happens in squall lines. So it's not like it's a uniformly distributed vertical velocity and everything goes up, but there are all these convective towers that are like bubbling up. And so if you were to look at a slice, you can see in these figures, you can see that the convective towers are more or less aligned, right, and close together, but there is a lot of heterogeneity in their distribution, in their spatial distribution. Now, let me just drink 1 second. Excellent. Okay. These convective parts can often take a nasty form and take the form of a bow. Bow. Let's say I'll say bow. A bow echo is a form of severe weather that is particularly dangerous. They're not as common as squall lines, luckily, but essentially they happen when the downdrafts are particularly intense. And the reason why these have the shape of a bow is that the downdrafts are so intense that when they come down, they push the convection out in a way. So the downdrafts come down and create these really intense cold pools. These cold pools lift new convective clouds, and these ones are a little bit more advanced compared to the other ones, just because there's this downdraft, this jet that is channeled down and has sort of pushed the air out in front, okay? Bow echoes are, as I said, they're not too frequent. They're less frequent than mesoscale convective systems, but these can create damages that can propagate for hundreds of kilometers. Bow echoes is a lot of precip, potentially fairly decent hailstones, and straight line winds at the surface. So, trees are coming down, houses are destroyed maybe. They're not as intense as tornadoes, obviously, or, particularly strong outflows. They are particularly strong outflows. I'm sorry. They're not as intense as tornadoes, of course. But I would also argue that tornadoes a pretty high bar for how intense things are. And so, bow echoes is one example when the convective part really takes itself a bit too seriously, and thanks to factors in the environment becomes a little too intense. As for the stratiform part, as we said, the stratiform part is generated by elements in the convective part that kind of die off and are left behind, right? The air is still slightly buoyant, and so it's still going up and condensing a little bit, but it's a lot weaker. Precipitation is a lot weaker. Vertical motion is a lot weaker. I would say I'm no aviation expert, but you can probably fly through a stratiform part without fearing too much. Clearly, you have to be careful to avoid the convective towers. So maybe just fly, around the MCS. And also, it generates this what is known as the mesoscale downdraft. Like precipitation is falling down, evaporates, generates a downdraft that, because precip is less intense, precip is less intense, the downdraft also is less intense, and this is known as a mesoscale downdraft. It's less intense, but don't be fooled by the smaller intensity, because while the convective downdraft is more intense, it is also more concentrated, right? Because, it has a radius of few kilometers maybe, if we're being generous. The rear inflow jet for the squall lines, or more generally the mesoscale downdraft for the mesoscale convective systems, this can be as big as long or as large as a few hundred kilometers. And so it has a decent size. On the radar, this is pretty interesting. This looks like a secondary maximum, behind the MCS. So here we're seeing the convective part, convective region that looks, it's a little bit arc-shaped, although this, I would say this is likely not a bow echo. Not all arc-shaped convective parts are bow echoes. Those are usually really big and require, though there's still a lot of disagreement on what makes a bow echo, but it requires a certain intensity. So all bow echoes are arced convective shapes, but the vice versa doesn't necessarily happen. So here we have an arc-shaped squall line, and behind it you see that there's like a pause almost, and a bit behind it there is the stratiform region. This pause is essentially due to the fact that you have these convective parts that are going up, and they are still precipitating, but also kind of not so much precipitating. They detach themselves from the main convective part and they kind of hang out there. And it takes a little bit before they pick up and they keep precipitating a little bit more, and they create this stratiform region. So this is a typical shape for the stratiform region. So you have the convective part, and you have a lot of red colors on the radar. Then there is a little bit of a pause, if you will, and behind it you have the stratiform region. Okay. Another way to visualize that is that particular scan was looking at sort of the plane view, but at one particular angle, okay? Just one scan at a particular angle. What I'm showing here, figure 947, is one particular direction, so not the plane view anymore, one particular direction, but you're scanning over all the angles. And so now you pick the horizontal structure, the vertical structure, of this squall line. So you can see here, and the contours are vertical velocity. Continuous contours, you can clearly see there is a lot of vertical velocity at the entrance. Below it, dashed contours, that's the convective downdraft. Red color, a lot of precip going on there. So this is, we get it. Like, this is what it is. Behind it, notice how vertical velocities become a lot dimmer. Precip also becomes dimmer. And you notice that there is sort of a pause right after the convective part, and then it kind of picks up again. And it's about 4 or 5 kilometers that you have, again, this precipitation maximum. Notice from the very end of the downdraft, you can kind of see this, this ghost of dashed lines that looks a whole lot like the mesoscale downdraft that comes in from the bottom, from the rear of the squall line, and it comes in. Again, just to clarify terminology, because maybe you're not too familiar, I often talk about squall lines because these are a very simple example of mesoscale convective systems. All squall lines are mesoscale convective systems, but not all mesoscale convective systems are squall lines. So just to keep, just a sort of fixed terminology here. The convective part is more intense in terms of rainfall. So you should expect the highest rainfall rates in the convective parts. However, the convective part is small and it kind of dies off pretty quickly. And so although it rains a lot, it doesn't rain for long. The stratiform part, it rains less. So you may have rain rates that are, 2-3 times less than the convective part, but it may last for many, many hours. More than the convective part. So they both contribute equally. Again, don't be fooled by the sort of the lesser magnitude. I don't know if this is correct English, but the lesser intensity of the stratiform part. The stratiform part is more like a marathon runner. Like, it doesn't mean that just because they're running slower than those who do like 100-meter sprints or whatever it's called in the sports world, just because they run less, it doesn't mean that they're not struggling compared to others. So this figure kind of confirms a little bit what we were talking about, where you have high precip in the convective part, vertical velocity, and the mesoscale downdraft. So this is just to illustrate even more what we were talking about. Again, if you want to pause, feel free, but otherwise I would move forward. And also, this is interesting because it's hard to, let's say like this. Mesoscale convective systems are made of two basic ingredients, the stratiform and the convective part. But as any person who's ever tried to bake would know, you can get different results according to how much of each ingredient you put in your recipe. In this case, one way that you could figure out how much of each ingredient it would be if you look at the heating rates. Now, heating rates, you should think, what is creating heating rates in these systems? Well, I would say mainly the release of latent heat by condensation and eventually melting, right? So heating rates, positive heating rate, likely a lot of condensation, negative heating rate, a lot of evaporation. In the left panel of this figure, you notice that the convective part has a pretty clear signal. The dashed line is a pretty clear signal that in the mid-troposphere, you have a big heating rate. And that tends to kind of overshadow. Sure, you do have cold pools, which means you likely have negative heating, so cooling rates closer to the surface. But on the other hand, there you also have, if you consider all the convective clouds and you average over their lifetime, there you may also have a lot of condensation. So the two may actually balance each other. And so the result, averaging over all the convective clouds you see over time, is just this one single mode and a maximum in the mid-troposphere. Stratiform region tends to have binodal, binodal. I think it's actually trinodal, right? Because there's like two nodes at the extremities and one node in the center. This structure where there's a positive maximum in the upper troposphere. This is where, parcel is going up, it's condensing, it's releasing a little bit of latent heat. And then as it goes down, it evaporates, and there's actually a substantial amount of the troposphere where evaporation happens. And so there you tend to have negative heating rates, so cooling rates. And so when you look at the total heating rates averaged over all the life cycle of a mesoscale convective systems, that could give you some idea of how much stratiform and how much convective part you had, because otherwise it's kind of hard to tell them apart. I mean, if you were to look at them, for example, from a satellite, you just see a blob. Clouds tend to have, the cloud top heights are kind of similar, and so it's this blob, whether you look at it from, IR, visible, it's kind of hard to distinguish. But if you were able to look at the heating rates, then that could tell you something about how much stratiform, how much convective you had. So this is also something that I mentioned to you before. Mesoscale convective systems or squall lines, they do kind of have different shapes. They can have different shapes. And obviously, when they start off and they're mostly made of convective parts, and as you then progress into their life cycle, the stratiform part get bigger and bigger. And when the forcing for the mesoscale convective system is done, and there's no more of that, then the stratiform part kind of dominates and it just kind of dies off. And so there would be more and more stratiform part the more mature the cloud is. And according to where you are on the planet and how the wind is blowing, you'd have different shapes. So, for example, if we were to, so if we look at this figure, LS stands for leading stratiform region, TS trading stratiform region, PS is parallel stratiform region. So what we think about when we consider squall lines is the one sort of at the top, if you will. So path number 1 is the most typical example of a squall line. Sorry, my throat hurts again. Jesus. It's like I can't talk for an hour inside of my house. I don't know why. Maybe these are the poltergeists that are affecting my throat. They're telling me to shut up. I don't know. But anyway, so path 1 is also the most common scenario. The numbers on each arrows represent how many, sort of the frequency, if you will, of squall lines that develop, of MCSs that develop that particular shape. You could have path also number 2, which is when the stratiform region leads, and there are slightly less of these. And then you also have the case where the stratiform part is kind of parallel, and there are a few cases of these, but again, as we said, they're kind of more rare compared to path number 1. This is pretty much what I had just said. So cartoons and conceptual pictures are simple, and they kind of help you to understand, but when you do look at these things on radar and you're out there doing weather forecasts, then it's, things are more complicated in nature, in real life, than they are on the conceptual pictures. So in particular, if you were to look at on the radar, as we said before, at the very initial stages, the squall line would look like a lot of isolated convective storms that are kind of bubbling up, okay? Maybe there is some kind of convective instability, a front passes by and lifts these cells, and these come up and create the first thunderstorms, for example, okay? Or maybe there's no synoptic variability and these cells are just bubbling up because there was a lot of CAPE and not so much SYN. These bubble up and they kind of, die off, and they start to create the stratiform region. And that's where it's key that there is some form of convective organization that creates new convective cells to then form a mechanism that kind of sustains itself. This is where you're intensifying. You're intensifying in the fully mature stage. You have a convective part that is really, really strong, and you have an equally strong stratiform region. In the decaying stage, the convective part is kind of dying off, and the stratiform region is still continuing because it's the remnants of those convective parcels that are dying off. But when there is no more convection, then there's no more way to sustain the stratiform part, and so that kind of dies off. You maintain like stratiform clouds with a little bit of drizzle, light precipitation. So on the radar, you'd see it becoming greener and greener until eventually it dissipates. This is a particular example from an MCS, squall line MCS, that took place a few years ago. And this tells you the total rain due to the different forcings, the different regions of the cold pool at different times. Notice that this system lasted, so these measurements and this system lasted for a good, 24 hours? Yeah, so 24 hours, which is highly non-trivial. Convection was, it kept going and increasing, it kept contributing and going unscathed for the first 12 hours. The accumulated rain keeps going up, meaning that there are new convective towers that are going on. And then on September 5th, the sort of the convective part starts to die off, and at the same time, the stratiform part also dies off. As we said before, don't be fooled by the fact that stratiform regions are less intense. They still contribute to a decent amount of rain. This final slide was to say that, again, like there are all these different life cycles. Think also in terms of how this system interacts with the radiation, because this is also going to affect the radiation that happens at the surface. When the mesoscale convective systems is getting started, not a lot happens. Clearly, cumulonimbus clouds interact with shortwave and long-wave radiations, but still we're on very small scales. When we reach maturity, then there is the stratiform clouds are thick enough to, and they're made predominantly of clouds, and so they typically sort of absorb latent long-wave radiation that comes out of the surface, and they emit themselves some long-wave radiation. After all, they do have some temperature. As the storm becomes more and more mature, then, and kind of sort of dies off, the convective part and the precip stops, and you're left with a relatively thick layer of cloud where you also have that shortwave radiation that is going up is blocked. So the cloud is no longer only opaque to shortwave, but longwave, but also to shortwave radiation. Then this kind of dissipates, and the sky clears. Okay, so this was pretty much all I wanted to tell you about mesoscale convective systems. There is a ton that could be said about mesoscale convective systems. It's a very rich area of research and really, really important topic for those who make weather forecasts. I will see you for next lecture. As usual, please feel free to reach out to me if you need anything, if I can help you with anything. If something was not clear in this class, shoot me an email, Skype me, text me, call me on Zoom, whatever. Otherwise, I will see you next class. Stay healthy and please stay inside.